There is Dr. Vamsi Mohan. In today's session, we'll be discussing about Poisson's ratio, volumetric strain. Okay. So, we know that when a member is subjected to unidirectional stress, it will be subjected to some elongation in the direction of stress. Okay. Consider some member of cross-sectional area A, subjected to a tensile force of P. Now the stress to which it is subjected is P by A. Okay. So at any section, the stress is force by cross-sectional area. Okay. So this member is subjected to some elongation in the direction of force. If L is the length, initial length, there will be some increase in length due to the tensile force, that is delta L. Now it is subjected to the tensile strain, that means increase in length takes place due to tensile force. So the strain in the direction of force is said to be the primary or linear strain, and that strain is given as delta L by L. Delta L by L. Okay. The linear strain is given as delta L by L. And this axial strain is accompanied by an opposite kind of strain in all the directions at right angles to it. It means as the length increases, there will be some decrease in dimensions at right angles to the axis, the length. For example, if the cross section is a rectangle of dimensions B and T, so there will be some decrease in thickness and decrease in breadth due to the increase in the length, okay, which takes place because of the tensile force P. Okay. If the force is compressive, let us suppose, if the force is compressive, what happens? If the force is compressive, then the length of the member decreases by some amount. Okay. So the length of member decreases, and what happens to the lateral dimensions T and B? So the strain is compressive now. The strain is compressive. Delta L by L is compressive because of this compressive stress force. Okay. So there will be opposite kind of strain. There will be opposite strain at right angles. What does that mean? There will be increase in dimensions at right angles. That means thickness and breadth will increase slightly because of the compressive force. Because of decrease in length, there will be slight increase in thickness and breadth. Similarly, if the bar is circular, there will be some decrease in diameter. Okay, due to compressive force along the axis, the cross section, which is a circle, the diameter decreases. Okay, in case of tensile stress, the diameter decreases. Okay, because the length increases and it accompanied by opposite strain, that means compressive strain in the direction of diameter. That means the diameter decreases because of tensile stress. Okay, this clear. And that strain which takes place at right angles to the linear strain is said to be secondary strain or lateral strain. Okay, yeah, that is which takes place in the direction perpendicular to the force. Understand? So if the member is subjected to uniaxial, in this case, if the member is subjected to biaxial or triaxial stresses, forces, then say sigma 1, sigma 2 and sigma 3, then because due to sigma 1, you will have increase in the dimension L1 in the direction of sigma, and there will be decrease in the direction of L2 and L3. Okay, due to sigma 1, there will be increase in length L1 and decrease in lengths L2 and L3 at right angles to sigma. Similarly, due to sigma 2, there will be increase in L2, increase in length L2 and decrease in lengths L1 and L3 at right angles to sigma 2. Same is the case with sigma 3. It means there is increase in length L3 and decrease in lengths L2 and L1 due to sigma 3. Okay, and these strains they maintain some constant ratio. Okay, the linear strain and lateral strain, they are the ratio of these two is constant, and that constant is said to be Poisson's ratio. For a particular material, the constant, uh, the Poisson's ratio is constant. Okay, for a particular material, the Poisson's ratio remains same. That means the ratio of lateral strain to linear strain is said to be Poisson's ratio. Okay, the linear strain is delta L by L and lateral strain is delta D by D in case of circular bar, and the ratio of these two, lateral strain to linear strain, is called Poisson's ratio and is represented by letter mu or 1 by m. Poisson's ratio is represented by letter mu or 1 by m, which is the ratio of lateral strain to linear strain. Lateral strain to linear strain. Okay, this is also represented by 1 by m. Okay, 1 by m is equal to lateral strain by linear strain. Yeah. So the lateral strain is now mu times linear strain. Okay, lateral strain is mu times linear strain. Okay, so let us see some numerical example here. A steel bar 2 meters long, 20 mm wide, and 10 mm thick is subjected to an axial pull of 20 kilonewtons in the direction of its length. Find the change in length, breadth, and thickness. The Young's modulus E is 2 into 10 power 5 Newton per mm square, and mu, the Poisson's ratio, is 0.3. As I told you, this Poisson's ratio is depending on material, it changes. Okay, for a material, it remains constant. Okay. Now, the bar is of length 2 meters. In millimeters, it is 2000. Subjected to an axial pull P of 20 kilonewtons, and the cross section of the bar is 20 mm wide and 10 mm thick. 20 mm wide and 10 mm thick. That is B, width 20 mm, thickness 10 mm. So the cross sectional area is 20 into 10. 200 mm square is the cross sectional area over which the force P will be acting. Okay. So the stress in the axial direction is P by A. Stress in the axial direction is P by A. Sigma is P by A. That is 20 kilonewtons. Convert into newtons, multiplying by 1000. And A is 200 mm square. So the stress is 100 Newton per mm square. 100 Newton per mm square. Okay. Now you can find strain. You know that Young's modulus is stress by strain, linear strain. Okay. You can find E as sigma by Young's modulus, stress by Young's modulus. That is 100 by 2 into 10 power 5. So what is the strain now? 1 by 2000 is the strain. 1 by 2000. You can directly find delta L using the expression PL by AE. Okay. The extension delta L can be directly calculated by using PL by AE, which comes out to be 1 millimeter. Okay. So strain is now 1 by 2000. Delta L by L. L in millimeters is 2000. So strain is 1 by 2000 or 0.0005. Okay. Now the lateral strain. This is the linear strain. Lateral strain. Lateral strain means maybe delta B by B or delta T by T. Okay. It is clear. So lateral strain by linear strain. The Poisson's ratio is defined as lateral strain by linear strain is given as 0.3. So what will be the lateral strain now? Lateral strain is 0.3 times linear strain E. Okay? Understand? That is 0.3 times delta L by L, which is 0.00015. Okay? Similarly, delta T by T is also same, 0.00015. Okay? So from this, we can calculate delta B and delta T, the change in width and thickness. Okay? Delta B is 0.003 millimeters, and T is 0.0015 millimeters. Okay, yeah. So this is one example. Another example, let us consider a metal bar of length 200 mm and cross section 50 by 50 mm is subjected to an axial compressive load of 500 kilonewtons. The contraction of the bar is found to be 0.5 millimeters and increase in thickness 0.04 millimeters. Find the Young's modulus and Poisson's ratio. So here the bar is given to be of length 200 mm and cross section 50 by 50 square bar. Okay, so breadth and thickness are same, 50 mm, length is 200 mm. So the cross sectional area is BT, the cross sectional area 2500 mm square. Okay, and compressive load is 500 kilonewtons. Okay, we convert this into newtons, multiplying with 1000. Okay, now what else is given is load is given, delta L, change in length is 0.5 millimeters, change in thickness is 0.04 millimeters. Okay, so how to calculate the Young's modulus and Poisson's ratio? So first let us find linear strain. Linear strain is ELC, in the direction of length. Linear strain is in the direction of length, EL. So which is delta L by L, that is 0.5 by 200 or 1 by 400. Okay, 1 by 400. Similarly, lateral strain in the direction of thickness or in the direction of breadth. Let it be ET and EB, both are same. Okay, that is delta T by T or delta B by B. In this case, the breadth and thickness both are same, being square section. So lateral strain is 0.04 by the thickness 50 mm. Okay, it is it comes out to be 1 by how much? 4 by 100, that is 1 by 25, 1 by 1250, 1 by 1250. Okay, so now knowing lateral strain and linear strain, we can calculate Poisson's ratio. Poisson's ratio mu or 1 by m as lateral strain by linear strain. Okay, that is 1 by 1250 divided by 1 by 400. So this is 400 by 1250. Okay, yeah, 400 by 1250. So it can be reduced to 4 by 12.5. 4 by 12.5. 1 by 3.11 or something like that. No, sorry, 1 3. 3.13. Okay. So Poisson's ratio is 1 by 3.11. 1 by 3.1. Knowing Poisson's ratio, how will you get Young's modulus, which is stress by strain actually. Young's modulus is stress by strain. So, yeah, linear strain is 0.0025. 1 by 400 means 0.0025. And lateral strain is 0.0008. 0.0008. And Poisson's ratio is 1 by 3.11, which is also 0.3. Okay, 0.3. And how about Young's modulus? Young's modulus is stress by strain, linear strain. So stress is P by A and strain, linear strain is 0.002. 0.002. Okay. Yeah. This gives the Young's modulus as 80,000 Newton per mm square. Okay. 80,000 Newton per mm square. Okay. This is how we solve the problems related to simple stresses. Okay. Now let us discuss about volumetric strain. Volumetric strain means the ratio of change in volume to original volume. Okay. So under the action of stresses, whether compressive or tensile, okay, the dimensions undergo changes. Okay, the dimensions undergo changes. The dimensions in the direction of force increases, and the dimensions perpendicular to the direction of force decreases. Okay, so whatever it may be, there will be some change in the dimensions of the member. So there will be some change in the volume also. The ratio of that change in volume to initial volume is said to be the volumetric strain of the member under the given forces. Okay. The change in volume is delta V and original volume is V. So the ratio is delta V by V is said to be the volumetric strain. Okay. Now let us consider a rectangular bar of dimensions L, B and T, length, breadth and thickness, subjected to say force in the axial direction P. Okay, and E is Young's modulus. E is Young's modulus. Okay, so for this member, the initial volume is before application of forces, the volume of the member is length, breadth into thickness, LBT. Okay, that is the initial volume. And once it is subjected to tensile force or compressive force, there will be some change in length, breadth and thickness. Okay, due to that the volume also changes. Okay, It may decrease or increase, okay, whatever. Now consider a tensile force P, axial tensile force P, due to which the length increases by delta L and breadth decreases by delta B, thickness decreases by delta T. L increases and breadth and thickness decreases. We have discussed already. Okay. So the volumetric strain. How to find the volumetric strain? To find that, first you have to find the change in volume of the member. Okay. Yeah. For that, first let us see the stress in the direction of force P is P by A, the cross sectional area. Okay, that is P by BT, and linear strain is stress by Young's modulus, because Young's modulus is stress by strain, so strain is stress by Young's modulus. Stress is P by BT divided by Young's modulus E. That is a linear strain. And if mu is the Poisson's ratio, then lateral strain is given as mu into linear strain, which is sigma by E. That is mu into P by BTE. That is the lateral strain. Okay. It is clear. Now, the change in thickness delta T is T into lateral strain. Okay, delta T by T is lateral strain. So delta T is T into lateral strain. So lateral strain already we have seen, which is lateral strain in the direction of thickness or in the direction of breadth as mu into P by BTE. Okay, yeah, this multiplied by T, that gives mu into P by B. Mu into P by B. T gets cancelled. So change in thickness is mu into P by B. Similarly, the change in breadth delta B is B into lateral strain. Okay, so that gives delta B as mu into P by T into E. Okay, mu P by T. Now B gets cancelled. Okay, so change in breadth is mu P by T and change in thickness is mu P by B. Okay, and what is the change in length? Mu PL by BTE. Change in length is mu PL by BTE delta L. Because linear strain is mu P by BTE, delta L by L is linear strain, which is mu P by BTE. So delta L is mu PL by BTE. We have already seen delta L by L. The linear strain is mu P by BTE. So what is delta L from this? Mu PL by BTE. Okay, that is the change in length. Now, the final length is L plus delta L, change in length. Here, change in length is nothing but increase in length because of tensile force in the direction of length. Delta L increases and breadth and thickness decreases. So, the final width and final thickness are given as B minus delta B and T minus delta T. So the final volume V1 is L1 into B1 into T1. The final dimensions L1, B1, T1. So L1 is L plus delta L, B1 is B minus delta B, T1 is T minus delta. Okay. Now, after expanding this, first let us take L, B and T common here. Taking L common from this, we will have L into 1 plus delta L by L. Similarly, B common from this, B into 1 plus 1 minus delta B by B, and T common from this, T into 1 minus delta T by T. So LBT into 1 plus delta L by L, 1 minus delta B by B into 1 minus delta T by T. So after expanding and ignoring negligible values, after expanding this and ignoring negligible values means the products of least quantities such as delta L by L into delta B by B, or delta B by B into delta T by T. Okay, delta T by T, the strain delta B by B, these are small quantities. When they are multiplied, it gives still smaller quantity. So the second order and third order terms are ignored. Okay, their values being very small, we neglect these products small values. So after expanding and removing these smaller values, ignoring these, you will get the final volume as LBT into 1 plus delta L by L minus delta B by B minus delta T by T. Okay. So the change in volume is now V1 minus V, the final volume minus initial volume. Okay. So which comes out to be LBT into this minus LBT. So LBT into 1 and LBT. These gets cancelled. The remaining term is the change in volume. Okay. And here LBT is nothing but initial volume. So delta V by V is equal to this. Okay. The volumetric strain here, in this you can take P by BTE common actually. P by BTE you can take common. Okay. You will have 1 after taking P by BTE common. You will have 1 minus mu minus mu. Okay. Inside brackets. So P by BTE into 1 minus 2 mu. 1 minus 2 mu. Okay. So delta V is equal to V into P by BTE into 1 minus mu minus mu. That is 1 minus 2 mu. Okay. It is clear. So the ratio of delta V by V is equal to P by AE into 1 minus 2 mu. P by AE into 1 minus 2. And what is P by AE? Nothing but linear strain E. Linear stress by Young's modulus. P by A means stress by Young's modulus. Stress by Young's modulus is nothing but strain. Okay. So delta V by V is equal to E into 1 minus 2 mu. Okay. It is clear. So that is the expression for change in volume. Okay. For a rectangular ball. Okay. That is volumetric strain of rectangular bar is given by this expression. Understand? Similarly, for other cross sections also we can find the change in volume. Okay. The ratio of change in volume to original volume. Okay. Now, let us see one example, numerical example. A bar of length 2 meters, breadth 2 centimeters, and thickness 1.5 centimeters is subjected to a tensile load of 30 kilonewtons. Find the final volume of the bar if Poisson's ratio is 0.25 and Young's modulus is 2 into 10 power 5 Newton per mm square. So final volume V1. Okay. So you know the volumetric strain delta V by V, which is given as E into 1 minus 2 mu. Once you know volumetric strain, you can find change in volume and hence the final volume, because initial volume is known, LBT. Okay, is this clear? Yeah. Okay. So the ratio of change in volume to initial volume is the volumetric strain. Okay. Now let us see one example on this. The bar of length 2 meters, you convert that into millimeters. Breadth is 2 centimeters, that is 20 mm. Okay. And thickness is 15 millimeters, 1.5 centimeters. That is 15 millimeters. Now the load 30 kilonewtons. Converting it into newtons, 30,000 newtons. Mu is equal to 0.25, sorry, 0.25. And Young's modulus is 2 into 10 power 5 Newton per mm. These are the values given. Now the initial volume we can find. Okay. Initial volume of the member is LBT. So 2000 into 20 into 15. Okay. So 60 into 10 power 4. 60 into 10 power 4 mm cube. Okay. And volumetric strain we can find directly by using the expression E into 1 minus 2 mu. That is P by AE into 1 minus 2. Because E is equal to P by AE. Now everything is known. We can find P. What is P here? 30,000 newtons. And area, cross-sectional area is 20 into 15. And Young's modulus is 2 into 10 power 5 into 1 minus 2 mu. Mu is 0.25. Okay. So how much is this value? 30. This is 300. So 1 by 2000 and this value is 0.5. So 1 by 4000 is volumetric strain, delta V by P. Or delta V is equal to 1 by 4000 into volume, initial volume. How much is that? 60 into 10 power 4. 60 into 10 power 4. So this comes out to be 4000, isn't it? 0.4. $600 by 150 mm square, mm cube, sorry. Volume, so it is mm cube. So change in volume is 150 mm cube. So what is the final volume? That you need to find. Okay. What is the final volume? Initial volume plus change in volume. Change in volume is 150. Initial volume is 60 into 10 power 4 plus 150. Okay. Yeah. This is the final volume. So the volume of the member increases by 150 mm cube due to the applied load. Okay. Yeah. This is all for today's session. Let us discuss one more topic in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.